Okay, so we have a specific heat problem here about a thermos bottle and also metal being placed inside of it. Now the thermos bottle is not relevant to the heat capacity, is not used in any way. We expect this to be a calorimetry problem. Now our focus is regarding the water. What we do have is the water's mass. We are given a mass of 0.150 kilograms of water at an initial temperature of 4 degrees Celsius. Now we shift our focus to the metal. The metal is given in 90 grams. We have to convert this into kilograms. Now if you recall that there are 1,000 grams inside every 1 kilogram, you expect to have a 0.09 kilogram sample of the metal. Now the degree of the metal is given in Fahrenheit. This has to be converted into something universal. To make the problem more easier, we convert it into Celsius. Now you would subtract 32 and divide by 1.8. You have an estimated 100 degrees Celsius. Now final temperature here of both the solution is given to be 294 degrees Kelvin. Most of our degrees are given in Celsius, so we will convert this. You subtract 273 from. Now we use water on the left half of the equation. We have 0.150 kilograms of water. The heat capacity for water is to be 4,180. Now we do know the final temperature of the mixture to be 21, so we assume the same for water. And the initial temperature is going to be 4 degrees. Now my final product from these will be 10,659. Now going on the right side for the metal. The metal has a mass of 0.09 kilograms. We have an unknown capacity. We do have the final temperature to be 21 and the initial will be set at 100 degrees Celsius. So we multiply all three of these numbers. And our final total here is 7.11 C. Now what we do is divide both sides by 7.11. And this should give you the final heat capacity. Being 1,499 joules, kilograms per degree Celsius. Now this question is focusing on the conservation of energy, and particularly here we have kinetic energy feeding into heat or thermal energy. Now the first thing to focus on is the fact that the mass of the bullet is given in 3 grams. Generally, when we perform these operations or equations, we convert these into kilograms. So we are expected to have a mass of 0.003 kilograms for your bullet. We are also given a heat capacity of 128 joules each kilogram Celsius. And also we are given a velocity for the bullet at 108 meters a second. Now generally this equation seems to be rather complicated to first understand. So in order to simplify it, we go from heat into kinetic energy. Now heat is designed to be the MCAT formula, while kinetic energy is half of your mass velocity squared. Now we're given more information in regards of kinetic energy, so we should start from here. Half of your mass being 0.003. Your velocity is squared in these problems, so 180 squared. So we are given 48.6 joules of kinetic energy. Now going to the left, we have the same mass of 0.003. We have the heat capacity being 128. What we are solving for is delta temperature. Now generally we multiply all three of these and we should get 0.384 delta T. From here, all we have to do is divide both sides by the 0.384. So our delta temperature here is expected to be 126.6 degrees Celsius. Now we have another energy conversion problem, but we have also calories involved. We recall that for each 1 kilocalorie, we have 4,184 joules of energy. We are given a total amount of 2,500 kilocalories. So we have a total amount of 10,460,000 joules. Now the second part is our human has a mass of 60 kilograms, so we're fine here. What we are given is a heat capacity of 4,184 joules each kilogram. Now our problem here is that our temperature, at least initially, is in 98.6 degrees Fahrenheit. So we had to complete this, or I'm sorry, convert it into Celsius. So you have the 98.6 minus the 32 divided by the 1.8. So we have 37 degrees Celsius. This is our initial temperature. The problem is asking for our delta temperature, or our final temperature. Now the easiest thing to solve this problem is just find the delta in temperature. So we assume we keep the 10,460,000 as energy into the 60 kilograms of mass times the heat capacity of the human being, and we solve for temperature here. So first thing we do is multiply the 60 by the heat capacity, and in turn we get 251,040 times delta T. Now the next step ideally is just to divide both sides by the 251,040. This includes also the 10 million number. This would give us a delta change in temperature being 41 degrees. 41.6 to be more exact, Celsius. Now a watt equals joules per second. Expect to see a problem similar to this in the test in regards of time, but for the time being you have 900 watts of heat energy, so we can convert this easily to 900 joules. We include time just as a precaution. This is your heat energy. Now, we are focusing mostly on a electric heater with water. We're given the rate for water's vaporization of being 2.26 E6 joules each kilogram. Question is, how many kilograms can we vaporize with that much energy? Now we assume to be in kilograms due to the fact that the derived units of vaporization is in joules kilograms. Now this equation tends to focus mostly on heat with the mass and the rate of latent vaporization. Now we're given 900 joules of energy. We have an unknown mass. And we have our latent vaporization rate. So generally, what we do is just multiply both sides by the rate of vaporization. So on the right, we have a complete cancel out. And on the left, I assume we will solve for mass from this information. So 900 divided by the 2.26 E6. We return with a mass quite simple, kilograms. So this last problem is rather interesting. We have a mass of 258 kilograms. Now the question's phrased rather odd. We can assume that it may be an alloy, but in reality they are still separate in their base components. Now iron represents 75% of the entire mass, while copper represents the remaining 25% of the mass. So the first thing we want to do is find the corresponding masses. So in the case for iron, you have 258 times 0.75. This tends to represent percentages based off decimal format. And we return with 193.5 kilograms of iron. Now in regards with copper, we have the same 258. In this case we have 25%. So we have 64.5. So let's recap now. I have 193.5 kilograms of iron. Now iron is known to have a heat capacity of 4.6 E2 joules each kilogram, while the 64.5 kilograms pertain to copper, and copper itself has a heat capacity of 3.9. E2 joules each kilogram. Now we're not given an initial temperature, but we are given a delta temperature of 305 degrees Fahrenheit. Normally you want to convert this into Celsius due to the fact of the units of heat capacity. So I have 151.6 degrees Celsius for delta temperature. Now we could treat both of these materials separately. They may be combined in one product, but we will add the sums later on of their respective energies. So in regards of iron, I have 193.5 kilograms with a heat capacity of 4.6 E2 with a delta temperature of 151.6 degrees Celsius. So I'm given 13 million joules roughly for iron. Now shifting our focus to copper. My copper sample was 64.5 kilograms with a heat capacity of 3.92 and the same delta temperature of 151.6 degrees Celsius. So here I have about 3.8 million joules. So if we add both of these figures together, my grand total I have something along the lines of 17 million joules. Now in regards of your test, anticipate 14 questions, multiple choice. Each question itself is worth 5 points for a total of 60 points or 60%. Now you will have 4 open-ended. Each of these questions are worth 10 points, and these will give you the remaining 40%. Now your total would be, of course, 100%. Now please show your work when it comes to the open-ended. You will be deducted points if there isn't a sufficient amount of work shown, especially for conversions and equations.